So, students, now we are in a position to talk about allowed transitions. As we have understood that when an electron is in some higher energy level and and it goes to some lower energy level, during that transition, what we see is that the expectation value of position is dependent on time. So we are able to mitigate a kind of situation here that when we find that the position, the expectation value of position is not dependent uh, on time when the electron is in the level, say this is level 1 and this is level 2. So here the time remains constant. Here the time remains constant. But once there is a transition either from ground state to excited state or from excited state to ground state, the expectation value of the position is found to be dependent on time, and that gives rise to what's called as oscillations and oscillating position or oscillating or vibrating position, and that shows the dependence of time, and during that period of time the electron radiates in the form of electromagnetic radiations. So from going from ground to higher energy state, it absorbs radiations, and from higher energy states to the lower energy states, it emits back radiation. So we had a clear insight in that video where we talked about this position expectation value, and if we encountered the probabilities in terms of A and B as function of time. If we rightly remember, by evaluating the integral, the two middle terms that we had in terms of position, they were dependent on time. So now, in order to find the frequency, what we need those quantities that are involved here. Now, if I have to calculate the chance a given transition will take place, the general condition that's necessary for an atom in an excited state to radiate should be the integral that we have from minus infinity to infinity, then x, then we have psi n and psi n of star and dx. So this integral should not be equal to zero. So this integral should not be equal to zero. And what we say here is that the intensity of the radiation should be proportional to this integral. Intensity of radiation. Okay, it should be proportional to it. Now, talking about the transitions for which this integral is finite. Now, if we evaluate this integral for a particular transition from say 1 to 2, and if we find a finite value, if we are able to find a finite value, we call this kind of transition then as allowed transition. So this thing is allowed, and otherwise, for which this integral is equal to zero, if we come out that this integral is equal to zero, then we call those transitions as forbidden transitions. Forbidden transitions. So to move ahead of it is taking the case of hydrogen atom. What we have in hydrogen atom, we have set of 3 quantum numbers, and these quantum numbers can be utilized to specify the initial and the final state that is involved in the transition from one level to another level. Now, if the principle, what we have in terms of quantum numbers is we have principal quantum number, and we have we have orbital quantum number, and we have magnetic quantum number. And we have already discussed these quantum numbers to some extent. And if I come up with this principal quantum number as say, for example, n1, orbital quantum number as l1, and magnetic quantum number as ml1, and respectively, to have those of the final state as quantum numbers as n, l, and ml. And if I come up with some general alphabet, say f, and this f is a representative of x, y, and z coordinates. Now, the conditions for the allowed transition can be written down. We can write down the condition for allowed transition by using the integral that we have written down. So what can we write down is, for what can I write out is, from minus infinity to infinity, the f, which is function of x, y, and z. Then I have psi n comma l comma ml, and what I have is psi n1 comma l1 comma ml1 star, and then I have dv. Okay, now if this whole thing that we have utilized for a transition between two states, where we have set of three quantum numbers, n, n1, l1, and ml1, and we have n, l, and m. And for an allowed transition, what is important is that this whole integral should not be equal to 0. And if this is not equal to 0, then those kind of things that are involved in evaluating this integral, they are allowed. So here we will have allowed transitions. And this integral is certainly over all space here. And if we take this f, if we take this f as x, or for example, the radiation would be that produced by the antenna lying on some x-axis, and at the same time, this wave function psi n l ml, if we go with it, psi n l and ml. For hydrogen atom, we know this wave function, and can be evaluated for this f that we have, the function of x, y, and z, for all pair of states that are that differ in one or more quantum numbers. So that should be the case, that it is out there and it can be evaluated. For all the states that are differing in one or some more quantum numbers. When this is done, what we find is that the only transitions between the states of different n. Okay, so different n is what? That's principal quantum number. That can occur are those in which the orbital quantum number, which is L, changes by +1 or -1. So change of this orbital quantum number has to be ±1. So you can have the transitions in which you have different n, the n's are different, and only those transitions are allowed where this orbital quantum number changes by ±1, and the magnetic quantum number, which is ml is the magnetic quantum number, and it changes by 0 or ±1. So this kind of change, the change in the total quantum number is not restricted. This is not restricted for n. There's no restriction for n. So you can have from any n to any other n, but when it goes to the selection rule for the allowed transitions, what is important is that the orbital quantum number should change by plus minus one, and the magnetic quantum number should change by zero or plus minus one, and the selection rule is requiring this kind of thing. So this is becoming a kind of rule, a kind of law for the transition that takes place in hydrogen atom, that this L that we have, it must change by plus minus one. And when it changes by this plus minus one, this atom is going to radiate. The atom is going to radiate. Means that we will have photons. The photon comes up and carries of the angular momentum, which by the way is plus minus h cross, equal to the difference between the angular momentum of atom in the initial stage to the angular momentum of atom in the final stage. So the classical the replica uh, uh, of photon with angular momentum plus minus h cross is basically the what we call as what we call left or right circularly polarized electromagnetic wave. So here we don't have any right or left. All we have is plus minus h cross. But in classical world we have we have left or right circularly polarized electromagnetic waves. So this idea uh, is very unique in terms of quantum theory. So what is clear from this, what we understand from this conversation is that it's not that all transitions are possible. That electron can have freedom to move from any state, any state to any other state. That's not the case. No, the electron is allowed to have some transitions, what we call as allowed transitions. And allowed transitions, we have seen that what is the condition for allowed transitions, and for the values that integral that we have had, if this integral comes out to be zero, those transitions are not allowed. So those transitions will never happen in hydrogen atom, where this integral comes out to be equal to zero. So with this, I would like to end this talk.